Hello. Hello. Okay. Okay, class. Okay. Okay. Yeah, sorry. So, hello, class. This is chapter 9. I'm dealing with axial load. In this chapter, we're looking to determine the deformation or the displacement of an axially loaded member, okay? Which is slightly different in terms of how we evaluate our deformation or our displacement. In regards to chapter 8. So chapter 8, we're given the relationship between stress and strain, whereby stress is nothing more than the force divided by the area, and our E is Young's modulus, or what we know as modulus of elasticity, and then our epsilon, which is our strain, is nothing more than a change in geometry, which is the change of the length divided by the original length. Okay. So what I just said here, just pretty much outlined here. Okay. Now, when you when you keep the relationship of the stress and the strain in mind, if a bar has a rectangular geometric formation, right, and is deformed elastically due to a load that's been applied to it along the central axis, what happens is there's going to be a distortion or some kind of deformation along this central axis. Okay, and we see that in figure 9.1 on page 412. So in other words, when you have a material, a bar in this case, and you apply an axial load, again, an axial load is nothing more than a force that acts perpendicular to the surface of which the force has been applied. Okay, so your axial load is always acting perpendicular to the surface here. Okay? And you have a diameter. It's been given to you. The length has been given to you. When you begin to extend this bar, right, it's going to actually stretch. Okay, which is denoted by these dotted lines. So typically what happens is your L now it gets longer, okay? And that's what we mean by elastically deforms, okay? So in this case I have it begins to elongate, all right? Now the diameter, of course, in response will decrease, okay? But keep in mind that your point B is held in place, and point A is pulled by force. Okay, so this place is typically fixed. You will pull in this area, or this particular section of the bar. Okay, so at that point we say point A is moving relative to point B. Okay, knowing that B is stationary. For more information, please look at figure 9.2. Okay, so if you want to look at how this material typically behaves elastically, we undergo the equation that's being outlined in the textbook, and this N is nothing more than the force. The N just means a normal force, okay? Multiplied by L divided by A over E. Again, that goes this relationship. This right here is force over area. Here's your E times your delta L over L. Okay, and if you solve for the delta, right, which is what we have here, you're going to get F times L over A times E, okay, which is what you see right here. Okay, now if you wouldn't be able to, the reason why we have this summation sign is if you're looking to understand how the material is responding internally at every point along the way, you use a summation sign. Okay, we see that in an example. Okay, I hope this helps. Please, if you have any questions, please let me know. Okay, so we just switch on to the example here. Okay, so example 9.1 in our textbook, page 417. We have this structure that's being fastened to a wall, right? points A, B, C, D of interest, and at point B, it has an axial load. Again, axial load is a force behaving perpendicular to the cross-sectional area. At B, it's 80 kilonewtons. At C, is 40 kilonewtons, and we have a compressive force at D to actually go the opposite way. Okay. So step one is to draw a free body diagram at every point of the way. Okay. So for this free body diagram, before I even start that, this information may be helpful here. Okay. This information may be helpful. So when you have axial load here, it's like when you have a structural bar here, and you're applying an axial load. Okay. If you do a cross-sectional cut, meaning that how does the material behave internally, right? And this is all in positive, so I'm pulling this side, I'm pulling this side. Therefore, to make it equilibrium, these two forces, they cancel each other out, right? Likewise, these two forces, they cancel each other out. So that's for normal force. For shear force, again, shear force is like nothing but the force is always parallel to the area in question, and this is in a positive notation. Okay, so I apply a sectional cut. We split them this way. The sectional cut from the force on the outside, of course, the internal force is going to be the opposite way to keep it in equilibrium, and it's going to behave this way. Okay, these are equilibrium, these are equilibrium. Okay, likewise for moment, this is a positive moment because it's a smiley face. Okay, and then when you apply a sectional cut, you want to keep it in equilibrium. So therefore, those forces are behaving this way internally. Okay. So we come here, we take that information, and we come here. Okay. So we apply a sectional cut right here. That's what you see right here. Okay. And we do that. As you can see, this force right here is synonymous to this force right here, because I made the sectional cut this way. So this is this F going this way, and the same thing as F going this way. Okay, so you follow that pattern, you never get lost. Okay, so again, use our equilibrium equation. Some of the forces in the x direction equals 0. Once you find out, you know your FAB, because your FAB is going in the opposite direction, positive, positive, negative, because this is going in that direction. When you do the math, you get FAB equals 50 kilonewtons. At point C, make another sectional cut right here. Okay, and then you draw that free body diagram, and this is what you see right here. Okay, when you do the math, this is what you get. At point D, you draw another sectional cut right here. Point D, another sectional cut right here. And you just grab this component. You see that here. This is what we're talking about here. And here's our FCD. 7 kilonewtons. We do the math, you get negative 70. Okay, kilonewtons. Okay. Now, our next step is to find the displacement. Okay, we're going to use our equation here. Again, this funny looking E means sum. Okay, so we're going to sum up all the forces. We're going to sum up all the displacements for each individual section, and that's FAB times LAB times divided by AAB times E, and that goes for BC, that goes for CD. Okay, since the bar has a uniform diameter, okay, so the area stays the same. And once you do the math, okay, at this point, this E right here is in the back of your textbook under A36 steel. Make sure you look under the SI units. Okay, and once you find this along this column, go across, and you will look under modulus of elasticity. Okay, elasticity, and you'll see 200 GPa. Okay, G stands for 10 to the 9. It's giga. Okay. So now, once we have the information, we do the math, and we get our displacement at point D to be negative 0.0891 meters. Okay. Now part 2 is asking us to find the displacement of B relative to C. And then we just find our force BC, which we already found already. Plug and play, and this is your answer. Okay. I hope this helps. Thank you very much. If you have any questions, please let me know.